So thank you for the invitation, and which one? Okay, just double check that. Okay, so you heard a couple of times data scientist in the title. Actually, only do statistics, so maybe this is a bit misleading, but you know, it depends whether you consider it being data science or not. So I just prepared an outline. So I'm gonna just explain what I am, who we are, and then a couple of things. So first of all, the company, it's mainly, as I said, statisticians. Most of us, or I think, let's say 95% of us are like also lecturers in a university or in another. And the team is composed by like about 10 people, some of them working 100% for the company, some of them like being lecturers at like 80% and working 20% for the company, and some of them being academics that work on a project basis. Myself, I first studied biology, and then I was just frustrated by the data analysis part when I had to do my master thesis and stuff. I decided to then study statistics. And this is also why I think I then ended up in the consulting, because I see how much you can help people with this kind of data analysis part. The clients, as I said, we do a lot of teaching. So like in my case, I guess 30% of my time is teaching in universities. We do help research groups with data analysis. Focus is on stats, but we also do other things. And we also help private companies and agencies in general. So today, you know, this is an unusual talk for me. I'm not going to present like a use case, the whole analysis, but when we discussed with Tarun and Thomas, we were thinking about, you know, how should we work? How should we collaborate with these people and stuff? Because everything in this case, in this data science support is new, so there is not really much that you can use. So someone was asking this morning to another presenter a question, how do you work? And the question is, we're still trying to find out, which I think it's the same for all of us. So the talk is gonna kind of like focus on that. So what's our role? What should we do? And how should we do it? And how should this evolve? And obviously, this is my point of view from mainly like doing statistical analysis, which can be quite different from other things, but I think there is like a common ground. So the use case I'm gonna use today, it's about tiger mosquitoes and the transmission of some viruses. So this is a project with some, to say it shortly, like biosafety officers. So the idea is you go to a nice place in the tropics, you come back, you feel sick, you get diagnosed that you got a virus. And then from the biosafety point of view, the problem is like, okay, if some mosquitoes that can carry these viruses bite you, what's the likelihood that someone in your neighborhood can also get this virus? So this is kind of like the problem that we addressed. So the problem was really the local spread of these viruses. It can be dengue, it can be chikungunya. This is something that is currently monitored in Switzerland. And obviously, if there is this risk, and if the risk is high, then there is a need of intervention, which could be chemical intervention, just to kill like the tiger mosquito populations, or other kind of interventions. So the gold standard approach to evaluate what's the risk would be you quantify the abundance of adults, and this is the way to do it is just someone called an operator goes there, sits down, and counts the mosquitoes that go there and try to bite him, her, within 15 minutes. This number is then put in another formula that is kind of like given, one of these R0 formulas that you might have known with COVID, spread. And this, in the end, gives you a risk. The newer approach would be you don't look at adults directly, but you collect eggs, which also is an indicator of abundances of adults. And you can do this by using this, they are called ovitraps. So it's simply mosquitoes go there, lay eggs, and you can count eggs. this is usually part of the common monitoring system, which is anyway on place. So this is like cheap information that it's there anyway, that you can use. And then obviously you can, going from eggs to adults, and you introduce again this in the formula that gives you the risk, and you can quantify risk. So if we compare now the gold standard approach, it directly quantifies the adult abundances, but is expensive and it requires an ad hoc effort, and the problem is also unethical. So whenever you got a problem with viruses, you don't want to send people out there and count mosquitoes that might carry this virus. So the newer approach, it does it indirectly, leverages on the existing monitoring system that it's anyway there, and then in the end also estimate these risks. Now the whole thing relies on having a function that essentially you give some x, the number of eggs you observed, and this produces a number of adult abundances that you can use to estimate your risk. Again, you're going to use this R formula to then measure the risk. This function, or this whatever you call it, might be a simple coefficient. You just say 10x 100 adults, or the other way around, just multiplying it, or it might be a very complex model. Obviously, it depends on what you need in terms of precision, when it's good enough, and also how you're going to use the model. Now, in this very specific case, some researchers came to us and said, look, we collected some data about X. We also collected the human landings, so these people sitting there getting bitten by this tiger mosquitoes. We did a simple correlation. We don't find anything. Can you do better? And the other thing is, there is a paper published where they used these generalized least squares. And we've been working with them with similar data sets, similar data, and we use these generalized mixed effects models. Now, going back to kind of like the aim of the talk, what's our role? So the first thing is obviously the cheapest thing you can do to help them a lot is already tell them, look, obviously simple correlation is probably not complex enough. The paper, they use generalized least squares because it's a time series and they look into that, but in your case, this is not a problem. And the generalized mixed effect models might be a good idea, but then it's a complex model. If you need to implement this, it could be difficult or difficult to maintain. So then the next thing would be, okay, who's going to run the analysis? Shall we run them? And in very many cases, that's the case. We really, it's more efficient if we run them rather than helping them doing the analysis. So the obvious reasons for the clients or researchers in general, it's the quality of the analysis is just obviously better done by professionals, and the efficiency. Obviously, you spend less time than them in doing that. Now, the hidden reasons for the, I'm thinking about from the researcher's perspective, it's they don't really think about the model validation. Very often they fit models, they look at like any summary, any goodness of fit measure, and they think, okay, this is the best model. But a very typical example, it's working with time series, and you know that in reality, the model will be used to make predictions on 1 month ahead. And so you should also include this in your model validation, right? Because if not, the validation is not really testing what is going to be in reality, and then you might prefer a model that is too complex that in reality does not work well. And these are all things that we do and we think about, and usually it's not something that researchers think about. Then the other thing that we do take a lot in consideration is, okay, you produce a nice model, but ideally in science, then other people should use your results. So once you publish them, are the other people going to be able to use that? Like because it's too difficult, or because it cannot be implemented in their place? A typical example in this kind of models would be when you look at the insects abundance, temperature plays a major role. So I can put temperature in my models, but 20 degrees in Switzerland means something, 20 degrees in Sicily, it's something completely different. So if I do a model which has temperature and I want to use it somewhere else, probably it's not going to work well. So I could say, okay, let's introduce like here, day of the year or something like that, that makes it more, that it makes it more usable somewhere else. And this is usually things that researchers don't think about, but we think that they're extremely important in terms of, the final scope of the publication. Is it just, it's always like kind of a question like, do you want to show that it works here? Or do you want to show people you can do this and you can use it anywhere else? And obviously, very often we come up with new ideas, and this is also something that it's not expected from researchers. They just want you to analyze the data, write the method sections for the paper, and they think this is all what you can do, but you can always come up with new ideas. For example, in this specific case, we said, there is like several steps before you get to risk. So you get X, you estimate abundances, you plug this in a formula, you get a risk. Why not getting data from actual local transmissions, so the risk itself, and just exit themselves? So you skip all the between steps and you build a model on that. So you can always, there is pros and cons for that, obviously, but it's very often you can just say, why don't you do this in a different way? And very often, because you come from an external point of view, it's much easier for you to do this kind of reasonings. And then obviously the publication process, it's much more efficient, simply because whenever there is criticisms about the analysis, it's much easier for you to reply the reviewers. Right, now going back to what's our role. So shall we always run the analysis? And for what we do, I think it might be different, but I've seen this morning that all the people also say we supervise them, we help them, but they do the analysis. In our cases, no. I think ideally it should be a mixture of the two. Some analysis, we do them, and then some other cases you say, look, take the code and everything I've done last year and try to use that to do your analysis this year, or of this new experiment that it's very similar. And obviously you have to support them when they run the analysis. And the other thing is you have to keep in the you have to have them on board when you do the analysis to explain them what you're doing. So there is this knowledge transfer that it's very important, that goes back to what's our role. So I think at this stage of kind of like this data science supporting scientific researchers, the most important thing that we have to do is obviously analyze the data for them, but it's also enhance their data-driven thinking. So very often when these researchers come to us, they don't know what we can do. Some problems might be easier and they can see what we can do, but in some cases it's very difficult to tell them what we can do. And so it really takes a lot of time to decide on what we're going to do and how we're going to do it. So I think that once they will be able and trained to think in this kind of like data-driven thinking way, then we can really exploit the full potential of data science in scientific research. And in general, if researchers, they don't get what we do, then they cannot communicate this to anyone else. Then is one of these papers that the researchers, they said, yeah, there is someone else that did something similar. I didn't understand anything of that paper. And this is not really something that makes science progress. Now, this slide is, I think it's very much statistics focused, but I guess it's also applies to other people. So what we can essentially, what researchers can learn from us, it's how to best collect data, how to best design experiments. And this is also, in my case, this is something I really learned in the statistical consultancy, the ETH, that there is always a mismatch between the design and what hypothesis people want to address. And there is a loss of money, effort, energy, anything that is huge. Very, very often you say, look, if your question was that, you should have collected the data this way. It is slightly different, but it's a different thing, because in this case, I can still that there is an alternative explanation to your problem, or maybe the methods used to analyze the data, they don't really want the data this way, but another way, and this kind of things. The other thing is, if researchers are aware of what you can do for them, then right now it's like they come and you first have to explain. In the future, it will be great if they come and they know much better. I would like you to do this. So you start from a much higher point, and you can also do much more interesting things. In my case, and also this is what we do, we do because I kind of like still feel part of the Seminar for Statistics working there, but it's very often it's what you tell people to do or what you do for them, it's a compromise between what it would be fully appropriate and what you know that they're gonna grasp, they can understand, they can write a paper on it and stuff like that. So the reason why I think we need to help people enhance this data-driven thinking is not just about better science and stuff, but it's also from the egoistic point of view that we can more interesting projects in the end. Now, just an example of this group here, this one of the tiger mosquito, we're doing several projects with them. So I said, let's just show you a few things that are benefits of this knowledge transfer of previous collaborations. So we wanted to test the efficacy, they wanted to test the efficacy of an insecticide. Based on our discussion of previous things, we are able to do a design which is exactly addressing the hypothesis we want to test. So we spend a lot of time in defining what you want to test. The first thing was the efficacy of the insecticide over time. Then it's like, okay, well, how do you measure efficacy? In what sense? And blah, blah, blah. And in the end, we had a lot of discussions, but in the end, we really had a design that was perfect to then really answer their questions. The data, the first time I got data from them, I was like, oh my God. You know, it's a lot of time coding data, cleaning data, and everything is error prone. So if you get the data that's already in a better shape, it's not just about less time for you, but it's also less, a lower likelihood that you will introduce mistakes in your analysis. And also data structure, you know, when you got this Excel sheets with very many different tabs and stuff, and then you should follow the naming, and then there is a problem in the naming. It happened to me several times that we took over an analysis that was done by someone else, and very often we found mistakes in this kind of like tabs naming and stuff that were relevant for the whole analysis. So in that case, we said exactly how we want the data and stuff, and then it's way less work for us, and I think it's also much less error prone. And in this project, those people, they're not fancy statisticians. So when we did the first projects, maybe we used a simpler method than we would. But in this case, it was about, you know, measuring this effect of this insecticide. And in the end, we said, okay, we're going to use a GAM such that we can define the effect as a smooth function that varies over time. So here you got the efficacy if you want. And on the y-axis, so on the x-axis, you got the time. And this was something that if we hadn't worked with them for a long time, we were not able to bring them, you know, this method and explain them how this works. This leads for me to a win-win-win situation, which means we get more interesting data sets, better data, more interesting cases, they get better output in terms of science and what they can publish, and also science. Science gets something which is applicable to more, like a wider range, and blah, blah, blah. Now, there is a couple of things. Do I still have some time, or shall I? I will go quickly then. Okay. So as I said, In our case, there is a lot of room for playing about defining what you're going to measure, how you're going to measure, which is maybe different from, you know, getting images and you can tell them, go back and measure, take different images. So we do invest a lot of time in understanding what do you really want to show and what's the really underlying process. This was my question to you, Francisca. In our cases, very often you really need to understand how things work, not in detail, but at least the intuition how things work, because you would use different models depending on what you want to show. We do communicate with them a lot, and in the end, we always produce this, you know, dynamic documents where the whole analysis is reproducible, is in a PDF, so they can redo them, and anyone else looking at the paper can also redo the analysis if they want. Right. Maybe the conclusions. So talking about, in general, I think that there is a huge potential. I mean, there is a couple of groups here that help ETH. I think they could be 10 times as many people, and it would still be beneficial for ETH. So the potential is huge, I think. I think right now in this phase, we should really invest a lot of energy in training people from, you know, researchers and to explain them what is feasible, and make this transition to the data-driven such that we can really use the potential. And I think it's our responsibility right now, because the easiest thing you can do when you help people, you do the analysis, you give them the results, and you say, that's it. It's much more difficult to include them, to explain them, and all these kind of things. But in the long term, it's just much more interesting for everyone involved. Yes, as I said, it's just interesting for everyone. I will get better data, I will get more interesting problems, they'll get better science, science get better things, and so on. So thank you very much. I'm done.
Thank you, Rana, for the very nice talk.
You're welcome.
So if there is maybe one question, so okay, I already see a raised hand.
So you say that you collect the data, and that's the plus that you have. You collect the data, and researchers, they get the help of understanding how to use the data. I'm a bit confused right now, because you say to get in a research program, you need to understand what you want to do. Therefore, you understand the data, you understand the task, and you understand where you go. I don't actually see why, and maybe is that, and what do you do with this data actually that you collect from them?
Can you elaborate on what is actually that you don't understand? Why you, can you elaborate on that, please?
So you say that you collect data, so that's
I mean,
your
I'm not
win
physically
for you.
there, right? They do that. Maybe I feel part of a research group when we help them, so I say we, but they doing that, right? I'm not doing the collection, data collection itself.
Yes, they collect it, then therefore they should understand it, because they are researchers, they are not fool.
Yeah, but you know,
Wouldn't that be better to invest in training research to understand their task?
Okay.
Okay.
Right.
Thank you.
Shall I also try to answer that one, or would you like?
No, wait.
We keep it. Okay.
So yeah, so
Right.
we have already a good starting question for our panel discussion, which is next. Huh?
Very specific to.
Yeah.
Okay, maybe one last question from Simon here.
Thank you for the talk. So it's partly to you, partly to Arends also. Both of you sort of like, let's say, proper doing statistics, and you even worked at the seminar. So I just wanted to ask, when you talk about experimental design and understanding and modeling, and in particular causality, how far are you with causal inference? Now, I'm an amateur here, but I found it interesting to read the book, like The Book of Why by Tujia Pearl. So I was half expecting to see some do calculus, or at minimum some causal diagrams somewhere here, but they're absent. Why?
I think it's like more a philosophical thing, this whole causal inference thing. In general, anything you do it's based on very many assumptions, right? Now, the point is, depending on what you want to say, you're more, and how your results will be used, you might be more confident, say, okay, I'm going to take these assumptions and just say that's all fine. In some other cases, like, the assumptions are done in causality, you might not feel confident with them. You might not feel comfortable. For very many things we do, the main point is to what extent is experimental. Because you can control some things, but you cannot control other things. Like this one, it's kind of like we are able to control when the treatment is done in the season, because we know that the season plays a role, but it's still out in the field. So there is very many things you cannot control. So you try to do your best to control everything, but you still have very many things that can influence your results, and you cannot control them. So depending how many things can potentially influence your results, then it's about wording that you would use in the paper. We do this a lot when people write the papers and we say, we demonstrated this. Then it's like, wait, I would rather phrase this differently and say, maybe it really looks like it's too soft, but just like the wording it's really important. Then obviously you can always use causal inference models, other approaches. I don't know, in very many, like in these settings, I don't see what would be the added value to do that. And then it's always, it depends on many things. Like, if you publish where people use these methods, it's one thing. If you publish in journals where people don't use these methods, then, You still can. But then there will be maybe just 2 reviewers that are fully against you just because you're using a non-standard method. And then you also have to take this into account, because it doesn't make everything much more longer, painful, and. You could, yes. Yeah. Okay.
So thank you very much, Anna,
You're
for the
welcome.
nice presentation and the discussion.
Thank you.